other web browsers. So that this okay. Hello. Sam, is my slides seen to you?
Yeah, it's not visible. You can
Okay.
see now.
Okay. So good evening, one and all present here. Myself, Krishna Prasad. So I'm here to present a small topic about the simple harmonic motion, a small class about the simple harmonic motion. So before going into the simple harmonic motion, we can we have to look at what is the motion, right? That is, motion is a process in which the body changes its position with respect to time. Okay. The motion of a body we always measure in meters. We know as persons we move from one point to another point. So what actually happens there is that our body is getting changing in its position with respect to the time. Okay. So and this change in position are of two types, like the displacement and the distance. So then comes a question, what is the basic difference between the displacement and the distance? So distance is the amount of the time, sorry, the total distance that you covered in the entire course of motion, and displacement is the total amount of distance that you covered in a specific direction. So that is the basic difference between the displacement and the distance in simple terms. That if you are saying that you started from your home and this is your friend's home where you want to go, and this is the shortest path, the straight line is the shortest path, and these are some other paths which you followed, or suppose this is one, the straight line is one of the path which you followed and this one is the another path you followed. So in the straight line it is clear that it is the shortest distance as well as it has a specific direction, but in the zigzag moment which you took on the second time is not that, it doesn't have any directions. So that what is the problem is that it covers the distance but it has no specific directions, hence it can't be considered as a displacement. But in the case of a straight line motion or a rectilinear motion, which means the motion in one dimension, that you will be treating the displacement and the distance as equal. Okay. Hello sir. Okay. And talking about that, we can classify the motions into two, that is regularly repeating motion and non-repeating motions. So one of the best examples for the regularly repeating motion is the it is also known as periodic motion. It is the sunrise and the sunset. So how the sunrise and sunset is happening across the globe, that is when the earth is rotating around the sun, in an fixed axis. So that, hello sir, so can you hear me? Okay. So when the sun is rotating around the earth, you know that due to the difference or of the, hello, so some disturbances is coming from my side. Hello,
Yeah, Krishna. Please.
am I audible to you, sir?
Yeah, it's audible. You continue.
Okay. So that is, if this is sun, since earth is rotating around the sun, and since it is also rotating in its own axis, we know that the day and night occurs. The time period of each day and night is 12 hours. That is, alternatively the day and the night is experienced for human beings, whether it is Sunday or Monday. That is, every time the day is for 12 hours and night is also for 12 hours, together the 24 hours constitute a single day. So this regularly occurs because of the repetitive motion of the earth around the sun, and also it since its rotation in its own axis, due to the rotation of earth in its own axis. That is how I am telling you this is a regularly repeating motion or a periodic motion. A periodic motion is always a regularly repeating motion. And the next thing is that talking about a non-repeating motion. So what is a non-repeating motion or a periodic motion? Sir, just let me clear it. Okay. So I'll tell you an example. That is, take the sparkle. Suppose this is that sparkle stick. Okay. So this is one of the atoms here. I am considering one atom here. So suppose if you lit the one end of the spark, which is ignitable, and if it is getting sparkling, you know that after sometimes these atoms, that is these sparkles which you see here, are the atoms that are ignited and that comes out of the sparkle. So that if this is coming out, it will follow a certain trajectory and motion, but this one here, that this chemical atom here, that need not to follow the same direction as this one followed. So the motion of the similar kind of the atoms within the same sparkle is different, so that we can say that this is a non-repeating motion. Okay, and that is the major difference between periodic and aperiodic motions. The next one is another kind of motion. I just, before clearly going into simple harmonic motion, I wanted to talk to you about oscillatory motion. So oscillatory motion is that kind of motion where it is getting executed between the maximum and the minimum displacements. So we, okay, in the childhood we all have swinged on a swing, right? So what happens while you swing? That is, you will go to a maximum displacement and then you will go to a minimum displacement, and you will be moving around a pivot point. You will be moving around a pivot point with a maximum and the minimum displacement. At the center it will be equilibrium point. At the center it will be equilibrium, it will be equilibrium point where no force is acting on it. Okay, the total force, let me represent it using Ft. So the total force acting on the particle which is executing oscillatory motion, that is at equilibrium, the total force acting on the particle is zero. Okay, and the next kind of motion or the main topic of today is simple harmonic motion. Okay, so talking about simple harmonic motion. Okay, so simple harmonic motion is defined as a motion in which restoring force is directly proportional to the displacement of the body from its mean position. So consider the given system, okay, where a spring is attached to a wall and another end of the spring is attached to a mass, and also assume the mass is at rest, okay, at x is equal to 0. And you also have to suppose that you are stretching the mass in this direction by the application of an external force, F external or Fe. Okay, you displace the entire system. I mean that you stretched the system to another point x1. Okay, so the distance from x to x1 is, let it be small x, just as shown here. Okay, so if you removed after stretching, I will just hmm, draw it here. You have to consider that dotted lines as spring. Okay, so after removing the force from x1, the applied external force, what you can see is that you can see the entire mass is getting back and forth, getting oscillated. So then the next question comes, why this is happening? Okay, so this is happening because when you stretch the mass from the position x is equal to 0 to x is equal to x1, that a restoring force, a force is getting stored inside the spring mass system in the opposite direction of the displacement. Let me denote it as Fr. Okay, that is the restoring force Fr. Okay, and that is the restoring force Fr, which is acting in the opposite direction. And if you are stretching this system to a quite a large distance from the equilibrium point, then also the system can retain its original position after oscillating. So what you can't stretch too much of a length, but within a given time period, sorry, within a given limit, you can stretch the particle and it will regain its original size and the shape. Okay, and that the particle will start to execute oscillations. Okay, and so the what I am trying to tell you is that in a simple harmonic motion, that is, its restoring force will be stored inside the system that will redirect the system into its original position. Okay, and also there it executes an oscillatory motion. I told you in the previous slide what is an oscillatory motion. An oscillatory motion is that kind of motion where the two particles get oscillates within the maximum and the minimum displacement, like in the case of a swing. Okay, and the next next characteristics of a simple harmonic motion is that its velocity is always directed opposite to the displacement or opposite to the external force. Okay, that I will tell you while I have to derive some derivations, so I will detailedly explain it to you at that point. Hello, sir. Okay, I hope I am audible. And the next and the next the thing I want to tell you about the simple harmonic motion is that we know that I told you within a certain limit, if you are stretching the string, that whatever be the distance up to which you stretch, that the restoring force that is getting stored on the spring will be directly proportional to the distance up to which you stretch the mass and also the spring. Okay, so that F is directly proportional to X, but you have to know that the since the restoring force is acting opposite to the direction of the displacement, that Fr is in the opposite direction of the displacement, so we need to give a negative sign here. We know that in order to avoid the proportionality constant, we need to multiply this using a constant called K, where it is called as a spring constant. In this case, it is called as a spring constant. So Fr will be equal to minus kx. Okay, so this is the at most basic things about the simple harmonic motion, and I will explain you how we can connect between the oscillatory motion and as well as the simple harmonic motion. Okay, so first of all, let me clear all these annotations. Okay, then the next thing is that I will simply explain you that is what is SHM is. So simple harmonic motion can be described as an oscillatory motion. The acceleration of the particle at any position is directly proportional to the displacement from the mean position, and I will tell you how this is related to, or how there is a component of oscillatory motion in a simple harmonic motion. Okay, consider our earlier system where a mass is tied to one end of a string. Okay, where you place the mass on a surface and you are applying an external force Fe. You're applying a force, external force Fe, and you stretched the particle to the distance x1 from x is equal to 0, and the distance between x equal to 0 and x1 is small x. Okay, so like I told you earlier, what happens is that when you, after stretching, suppose you took the mass into this point. Okay, then if you made the external force, or if you take out the external force from the mass, then what will happen is that the particle will start to oscillate. What I meant is that if it has traveled this much distance, if you stretched it by small x distance, if you changed the force from here, it will come back to its original position and also will start to go this same amount of distance in this side also. Okay, so what I am trying to tell you is that if you took this as a maximum displacement and this as a minimum displacement, the same distance will be covered by the mass in between the in the both sides of the equilibrium point. Okay, so that is what is a oscillatory motion, a kind of motion where a maximum and a minimum displacement is present. I hope I am clear up to this. Hello. Then the next thing I wanted to talk about is that now we talked about simple harmonic motion as well as the how a simple harmonic motion can be explained in terms of an oscillatory motion. Okay, so then a question arises that is all oscillatory motions simple harmonic? Are all simple harmonic motions oscillatory? Okay, so I will start answering by the from the second part, that is all simple harmonic motions must be oscillatory in order it to be simple harmonic, or in another words, if a motion has to be simple harmonic, then it has to be oscillatory. Okay, so then the another question comes, is all oscillatory motions are simple harmonic or not? Okay, so I think on my figure there is this annotation. Let me clear that. So consider a fan rotating with a constant angular velocity. Okay, a fan is getting rotating with a constant angular velocity. So the speed of each of the leaves will be the same. Speed of the each of the leaves will be the same, and it will be a periodic motion. Okay, and it will be moving within the maximum to the minimum displacement. Okay, and it is an oscillatory motion also. Okay, it is an oscillatory motion also, but if you change the speed, then it is need not to be a simple harmonic. Okay, sorry, hello. Okay, hello sir, can you hear me? Okay, i'll, I'll take the class. Okay, so if the fan is rotating with a constant angular velocity, then we can say that the fan leaves of this fan is rotating with a constant angular velocity, and they are covering equal distance in a given interval of time. So the motion is oscillatory, but it is not a simple harmonic motion since there is no restoring force which is acting on that. Okay, and the next thing I want to talk to you about is oscillatory motions is also called as harmonic motions, and all the oscillatory motion wherein most important one is the simple harmonic motion. Okay, and the another thing is that you know that is in an oscillatory motion there happens to be a maximum and as well as a minimum displacement. So the entire movement of that particle which is executing the oscillatory motion is sinusoidal in nature, which means it is having a maximum and a minimum displacement, and hence you can you can represent the displacement of that particle using any sinusoidal functions such as sine functions or the cosine functions. Okay, so I have represented here the moment of a particle in the terms or in terms of a sine function where x is equal to a sine omega t plus phi. So I will just briefly introduce the terms. Later we have to study about this in detail. A is the amplitude, omega is the angular frequency, t is the time, and phi is the phase. Okay, and the next thing, why we are studying simple harmonic motion, or what is the use of studying simple harmonic motion? That is the first question you need to answer while you are starting going to study about simple harmonic motion. Okay, that is simple harmonic motion is very useful and forms an important tool in understanding the characteristics of sound of waves, light waves, and alternating currents. That is the simple harmonic motion. Especially, I would like to tell you that the theorem of superpositions related to the waves. That is, suppose this is wave 1 as well as this is wave 2. Okay, so both of them are traveling in the same direction. Okay, let this be y1 and y2. If both of them got superimposed at some point of time and formed a wave called as y, then y will be the sum of each individual waves y1 plus y2. Okay, y will be the sum of each individual waves y1 plus y2. So this theorem is applicable when you talk about optics in the in the case of the interference, also in the case of electrostatics, wherever it is needed, this can be. That is the theorem which is related to the simple harmonic motion and the waves is applicable at any point in physics. Okay, the next thing is that any oscillatory motion which is not simple harmonic can be expressed as a superposition of several harmonic motions of the different frequencies. Okay, any oscillatory motion which is not simple harmonic motion can be expressed as a superposition. Like I said, that these can be expressed as y1 plus y2 of different frequencies. Suppose I'll tell you two instances. Okay, so what I'm trying to tell you is that suppose the frequency of this wave is 50 hertz. Okay, this one is 60. If both of them got superimposed, then the resultant wave will be just like this. Y is equal to y1 plus y2. The resultant waves will be the sum of both y1 and y2. Okay, then moving into the next point, that now we talked about what? We talked about different kind of motions, that is periodic motion. What is periodic motion? A periodic motion is a regularly repeating motion as a periodic motion, and next is the oscillatory motion. The another one is the simple harmonic motion. Okay, now we will go to the differences between, what are the differences between all these types of different types of motion. We will be studying that one. Okay, so what is a periodic motion? A periodic motion is a motion that repeats itself after an equal interval of time. Like I said, the alternatively the day and the night is there due to the rotation it is experienced for us due to the rotation of earth in its own axis. Okay, then uniform circular motion as an example, and the oscillatory motion is the to and fro motion of a particle about an equilibrium point, in which the particle moves on the either sides of the equilibrium or mean position is an oscillatory motion. And the next one is SHM. SHM is a special case of simple harmonic motion where that the particle moves between the two straight lines between the extreme points, and in a periodic motion there is no equilibrium point. That is, in a periodic motion there is no equilibrium point. It's a kind, and oscillatory motion is a kind of periodic motion bounded between the two extreme points. Okay, that we talk like in the case of, okay, we talked in the case of swing, as well as I hope you know about the simple pendulum also. This is the case. Okay, and the simple harmonic motion, the path of the object needed to be a straight line, and there is no restoring force which is acting on a periodic motion. That is, in a periodic motion there is no restoring force acting on that, but in a simple harmonic motion there will be a restoring force that is directed towards the equilibrium position or a mean position. Okay, and the oscillatory motion, the object will keep on moving between the two extreme points about a fixed point called a mean position. It is sometimes also called as pivot point. The equilibrium position is along any path. The path is not a constraint. Okay, that is, I hope you can see here. That is, in the case of simple harmonic, in the case of simple pendulum, we usually draw an equilibrium point here. Okay, and in the case of a periodic motion there is no stable equilibrium position, but mean position in a simple harmonic motion is a stable equilibrium. That is, what I meant is that is, in a simple harmonic motion there is a stable equilibrium position, which means that the external force that is acting on the particle at the equilibrium point will be zero. that is F external is equal to 0. Okay, and in the case of an oscillatory motion, there will be a restoring force that is directed towards the equilibrium position or a mean position. Okay, and that is, in an oscillatory motion, the net force on the particle is 0 at the mean position. That is, if we were talking about the simple pendulum itself, or in the case of swing, when we start oscillating from this point, suppose this is the minimum displacement. Let me draw it as minus a to a maximum displacement of plus a. So after reaching from minus a to plus a, the particle, or the, in the case of a simple pendulum I am talking about, so the particle is not resting there, it comes back, which means that is, in this kind of oscillatory motion also, there is a force that is getting restored, or that helps the particle to come back to its original position, and it acts against the direction of displacement. So there is a restoring force which is acting in the oscillatory motion. Okay, and the mean position is a stable equilibrium position for an oscillatory motion. The mean position is a stable equilibrium position for an oscillatory motion. And the next thing I wanted to talk to you about is the different kind of types of simple harmonic motions. Okay, so there are two kind of simple harmonic motions, that is the linear simple harmonic motions as well as the angular simple harmonic motion. What we will be doing is that we will be, hello, okay, we will be deriving the equations of motion for both kind of, sir, I think I'm having an echo here, but I will continue. Okay, so both of the, we will derive an equation for both types of simple harmonic motions. Okay, the first type I want to talk to you about is the linear simple harmonic motion, where the simple harmonic motion is occurring in a straight line. Okay, that is the our earlier example, the example of the spring mass system. If you apply an external force, that this mass will get stretched, and I hope you already will be knowing that if that external forces took from that position where it is stretched up to which it is stretched, then the particle will start to oscillate, and this oscillation is happening in a one dimensional, or this simple harmonic motion is happening in a one dimensional. So this kind of simple harmonic motion is known as linear simple harmonic motion. Okay, and the conditions for the linear SHM, we abbreviate simple harmonic motion as SHM. Okay, so that is, the restoring force must be acting opposite direction to the displacement, and also the acceleration of oscillation must be also acting opposite to the direction. Okay, so since f is directly proportional to minus x, we can multiply it using a constant, and we can write it as f is equal to minus kx. Okay, where that K is called as the spring constant. I hope I am clear up to this. I made you clear up to this. Okay. Then, in order to derive the equation of motion of simple harmonic motion, we need to consider a mass that executes a simple harmonic motion like as shown in the figure. Okay, I'll show you the figure. So the x0 is the mean position and v0 is the initial velocity at a time t equal to 0, and at a time t equal to t the particle is being stretched, it is the velocity is v. Okay, and v0 be its position at p, that is a distance now from O. At time t equal to 0, the particle is moving towards the right. At time t equal to t, the particle is at Q. That means the particle is getting displaced into the point Q. Okay. So, since we need to derive the equation, that let F be the torque force that is acting on what? On the oscillator. So from our earlier condition, we know that F is equal to minus Kx, where K is the spring constant. Okay. From Newton's second law, we know that F is equal to ma. Okay. So we can substitute this condition in the equation number 1, where ma is equal to minus Kx. We know the acceleration is the second derivative of position. Okay, acceleration is the second derivative of position. So the equation changes into minus m d square x by dt square is equal to minus kx. Okay, so what we can do is that we can write it here. So I can take the whole term from the RHS to the LHS. So I will write the equation here for your convenience. So m d square x by dt square plus kx is equal to 0. Okay, and let it be equation number 2. Okay, so the basic form of a second order differential equation is that d square x by dt square plus ax must be equal to 0. So in order to make the coefficient here 1, we will divide the entire equation, EQ equation. Let me erase this, either or many of you may get confused. Okay, so we are going to divide equation 2 throughout by m. So what will happen? This one divided by m, this one divided by m. So what will happen? This m, this one will be cancelled, and the equation changes into d square x by dt square plus k by m x is equal to 0. So what we are going to do is that this term, the term which I encircled right now, that term k by m, we will define it as a new term, that it is omega square. Let it be omega square. So omega square is equal to k by m, and from this we will get omega is equal to root of k by m. So the constant which we introduced here, or the term which we introduced here, is angular frequency omega. So it is the square root of the spring constant as well as the mass. So we will substitute this relation into this equation. Let me erase the lower part. Let me get the pen. So what will be change? What? So the equation which I underlined now, that will be changed into d square x divided by dt square plus omega square x is equal to 0. This is a second order differential equation, and this second order differential equation is having a solution of x is equal to a sine of omega t plus phi. Okay, so we got a solution for the equation of motion of linear simple harmonic motion, and now we will be detailedly studying about each and every terms that are present in this equation. Okay, so I hope you can see that we are having a solution here, and let me introduce you the terms. X is the displacement, a is the amplitude, and omega is the angular frequency, and phi is the phase. Okay, and before going into that we need to talk about the mean position or the equilibrium position. That is, mm, let me clear the drawings for you. Give me a minute. We know, in the case of a simple pendulum, okay, not simple harmonic motion, a simple pendulum, there will be a point where it is at equilibrium, where the total external force acting is 0. So that point where the total external force acting is 0 is known as the mean position or the equilibrium point. I hope you are clear now. Then the next main point is that amplitude, that A in the A here. So what is amplitude? It is the maximum displacement of a particle from its mean position. That is, if you took a particle here, okay, what is, suppose some waves are coming, okay, that is imparting some energy to this particle. So this is a string, okay, you have to consider this one as a string, then you will be definitely knowing about what I am talking. Okay, so when a wave is imparting energy on this particle, it will get displaced like this from its equilibrium position. Okay, equilibrium position where earlier it was present. So this height, okay, the maximum height that is traveled by this particle from its equilibrium position to this height is been termed as amplitude of simple harmonic motion. Okay, and the next one is the time period and frequency of a simple harmonic motion. Okay, that is, the time period is the minimum time after which the particle keeps on repeating its motion, is known as time period. Okay, and the smallest time that is taken to complete one oscillation is also defined as the time period. That is, or in simple terms, the time required to complete one cycle of motion is time period. Okay, and the time period t is defined as given as t is equal to 2 pi by omega or omega equal to 2 pi by t. Okay, and the next point we want to talk about is that the frequency of oscillation is the number of cycles per second. Okay, or the number of oscillation that occurs per second. So I will give you a simple calculation for this, that we know the human heart beats for 72 times in a minute, right? So what, how many number of times does the human heart beats in a second? For okay, so what we need to do, that's 72 times in a minute for a second, 72 divided by 60. So whatever be this quantity, this much number of times the heart must have beaten. Okay, and that is what the concept of frequency is, and the frequency is usually denoted by nu, that is equal to 1 by t, and the hertz is the unit which is used to measure the frequency. Okay, then talking about the relationship between angular frequency and the frequency. So we know from here itself, that is omega equal to 2 pi by t, right? Let me 1 minute. 2 pi by t. So from here itself, we know the relationship nu is equal to 1 by t. So we can rewrite the equation as 2 pi multiplied by 1 by t, or omega is equal to 2 pi nu. Okay, since this omega is angular frequency, okay, since this is angular frequency, we use the unit of radians per second, radians per second, to measure the angular frequency omega. And I already told you the unit of frequency is hertz. Okay, moving into the next term, phase in SHM. What is the phase of a wave? Which are the in phase wave, which are the out of phase waves? These are the points which we need to talk. Okay, so let me clear the drawings first of all, or else it will be creating some problems. Okay, so the phase of a vibrating particle at any instant is the state of vibrating or oscillating particle regarding its displacement and the direction of vibration at the particular instant. So what is that we will understand from this statement, or what is that we have to grasp from this statement? That is, suppose a particle is getting vibrating. Sorry, let me clear it first of all. I will draw a neat diagram. Suppose a particle is vibrating. Maybe I will draw the wave itself. Okay, and we usually specify that the wave is moving from one direction to the another direction, and it is moving, it is ahead of this particle, or else what you have to what I will tell you, I will tell you one thing, that suppose there are two ants. Okay, there are two ants, and both of them were on the banks of a pond. Okay, so when one was very close to the water, a stone was fell down and it took the ant with it. So you will be knowing that usually ripples will be produced when the stone is fallen on a water, just like this. Okay, so what will happen, that this ant will have to move through the crust and the trough, and the crust and the trough of the wave. Okay, so suppose you also have to suppose that after falling the first ant, the second ant also jumped in to save the first one. Okay, so assuming that the first ant is here, now what I have drawn is here, and the second ant that jumped to rescue the first ant is here. So what is that? That it jumped after some quite sometimes. Sorry, little late after this. Okay, so from the figure itself, we know that the direction of motion and the displacement of both the particles are being, or sorry, both the ants are being different, right? So the phase of a wave tells you which is the direction of motion and how it is moving. Okay, so this is the equation of the displacement, where the term phase is also getting added, where omega t plus phi will give you the phase of a particle, and phi is known as the phase angle. Okay, and when you put t is equal to 0, we will be knowing that x is equal to a sine phi. So this phi is known as the initial phase. Okay, and hello, I hope I'm audible to you. The next thing is that the phase difference. The difference of total phase angles of two particles executing simple harmonic motion with respect to the mean position is known as the phase difference. The two are vibrating particles are said to be in the same phase, and the phase difference between them has to be an even multiple of pi. Okay, so let me explain this to you. From our previous examples of ants, what you have to know is that suppose there was a third ant, okay, that is still on the banks of the pond. Okay, so he is observing these two. So like I told you, one is here and the other one is here. So if he is observing, or if he is, this is the initial position with respect to this position, or with respect to this ant, both of the ants are having different directions of motion, and that difference is known as phase difference. Okay, one is in the crust and another one is in the trough. Okay, that is known as the phase difference. I hope you understood it. And delta D is equal to R n pi, and if the two particles has to be in phase, the phase difference between them has to be in the terms of R n pi, where n has to be an even number, and two vibrating particles are said to be out of phase when it is in the form of 2n plus 1 pi. Okay, I will show you the in phase and out of phase waves for a little bit more clarity. This is an in phase wave, that is, you may be only seeing one, so I will draw here. Suppose this is wave A and this one is wave B. Okay, where the crest coincide with the crest, where the trough coincide with the trough. Okay, and also the direction of motion is also the same. So the waves A and B can be termed as the in phase wave. This is the out of phase wave. Okay, where you can see the crest is not coinciding with the crest, and the trough is not coinciding with the trough. And there is another version for the out of phase wave, which is the completely out of phase wave, where you can see that the crest of A is coinciding with the trough. Okay, so depending upon the superposition, that if the both waves are in phase, if they superimpose, their resultant wave will be a wave which is having higher amplitude and a higher intensity than the earlier two waves. Okay, that I meant these two parent waves. And in this kind of waves which are just out of phase, the resultant wave will be having a lesser amplitude and lesser intensity. Okay, and in this kind of wave, that is the third kind of wave where it is completely out of phase, that if these two waves superimposes each other, it will be a null wave, that where there is no amplitude and there is no intensity. A and I must be equal to 0. Okay, this is all about linear simple harmonic motion. Then, talking about the angular simple harmonic motion, let me clear the drawings. Okay, if restoring force was helping the particle to regain its original position in the case of a linear simple harmonic motion, then in the case of an angular simple harmonic motion, it is the restoring torque. Okay, it is the restoring torque. The restoring torque or angular acceleration acting on a particle should be always proportional to the angular displacement, and it must be directed opposite to the direction of angular displacement, or it must be directed towards the equilibrium position. Okay, so consider, let me explain that point to you. Okay, consider a simple pendulum which is hung like this at a mean position, from a mean position. Okay, suppose by applying an external force, if I displaced the particle into here, then with respect to the mean position, it has traveled, or it has swept an angle theta. Okay, so then the restoring torque T must be acting in the opposite direction of the displacement, or T is directly proportional to minus theta. Okay, that is the condition for angular SHM. And sorry, and now we are going to derive an equation of motion for an angular SHM. Hello, sir. Hello. Hello, sir. Am I left from the meeting? Like, okay. I hope I am still here. Hello, sir. Can you hear me? Someone please respond. Okay. I hope I am here. And talking about the equation of motion of angular displacement, that a body is free to rotate about an axis and can make angular oscillation. That is, we need to uh, think of an arrangement like this, like a torsion pendulum, where a body of mass m is hanged from an equilibrium point using a thread or a copper wire. Okay, for example, a photo frame of calendar is suspended from a nail wall. Okay, slightly pushed to its main position and released. That means it is just twisted and it is released. So then what will happen, or how it executes the angular oscillations? That is the thing we need to find out. Okay, and we know T is directly proportional to theta, and T is equal to minus k theta. We already know that the restoring torque is equal to I alpha. The tau is equal to I alpha, and we know if we substitute the equation, sorry, I has to be here. Okay, then I alpha must be equal to minus k theta. Okay, then what we need to do? We know the angular acceleration is the second order differential of angular displacement, that is d square theta by dt square. Okay, so substituting for alpha, I d square theta by dt square is equal to minus k theta. Take the k theta into the RHS, then I d square theta by dt square plus k theta must be equal to 0. Okay, then like I told you earlier, we need to make this coefficient to be 1. So divide the whole equation using I, then d square theta by dt square plus k by I theta is equal to 0. Okay, then we can substitute for this k by I as omega square. Omega square is equal to k by I. Let me erase this parts so that we can write the last equation. So the equation, the underlined equation becomes d square theta by dt square plus omega square theta is equal to 0. ഇതാണല്ലോ, sorry, this is the last equation, and hence the solution will be theta is equal to theta 0 sine of omega t plus phi. Okay, hello sir, uh, can anybody hear me?
Yeah, Krishna.
Okay, so should I be continuing?
Yeah, please continue.
Okay, so now we know this is the solution for the angular SHM. Okay, and so can you see my screen? No, I will reshare it again. So can you see my screen now?
Yeah, it's visible.
Okay. So the next thing we want to talk about is that the velocity of a simple harmonic motion, and the equation for the simple harmonic motion, that is how, or else you can say how the trajectory of that particle which is executing simple harmonic motion is being determined. Okay, so first of all, let me mark this part where we can write the entire derivation simultaneously. So first of all, our first aim is to find out what is the velocity of the simple harmonic motion. So we know the velocity is the first derivative of position, so that x is equal to a sine of omega t plus phi. Okay, then we already know v is equal to dx by dt. So we have to take d by dt of x, that is a sine of omega t plus phi. So we know the amplitude is a constant. So what we can do? Hmm? We can take out take it outside the differential, and we can write it as a d by d a d by dt of sine of omega t plus phi. Okay, then we need to differentiate the sine of omega t plus phi. We already know the differential of sine theta is cos theta, hence the differential t plus phi. Sir, it is showing that my internet connection is unstable. Just give me a minute to check it. What I will do. So let me connect the cable to this. Okay. 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 So and so this is the first part, first differential of the sine omega t, and let me give you an idea that while you write d by dx of sine x, what you are actually doing is that you are taking the differential of the sine function, that is cos x, and also you are writing the differential of this x also, this one also. Okay, hence this is dx by dx, which means that since the numerator and the denominator are being the same, this is 1, so usually we don't write that. Okay, so inside here you can see it as omega t plus phi. We assume that the phi is a constant, and we need to take the differential of d by dt of omega t plus phi also. Okay, so I already told you we are assuming that phi is constant, hence the differential of phi will be 0. So d by dt of omega t plus phi. So d by dt of omega t plus d phi by dt. So since this is a constant, we don't need to bother about d phi by dt. We have to take out the omega, and there is a t only. So then it will be omega dt by dt. Omega dt by dt. Since dt by dt is equal to 1, we only want to know about which one. We need to only add an extra omega here for the differential of omega t plus phi. So here comes that omega. Let me erase this part first of all. Omega a. Then we have to write the differential of sine, right? That is cos omega t plus cos omega t plus phi. That is cos omega t plus phi. For the convenience, we choose that phi is equal to 0. So if you want to choose phi is equal to 0 here itself, here itself you can do that, or else in some of the textbooks it is chosen after the differentiating. Okay, then this is omega a cos omega t. So we know what is the relationship between sine square theta and cos square theta. That is sine square theta plus cos square theta, sine square theta plus cos square theta is equal to 1, right? So we can rewrite this relationship in the terms of omega t. So what it will be, sine square omega t plus cos square omega t must be 1, or else the cos omega t must be equal to 1 minus sine square omega t and the square root of the term in the RHS. Now, okay. So after writing this, I will rewrite the equation here. Okay. Then let me rewrite this equation here. It is rewritten as omega a cos omega t. Sorry, I need to rewrite that equation, right? So root of 1 minus sine square omega t. Okay, so since x is equal to a sine omega t, we can substitute for sine omega t from this equation as sine omega t is equal to x by a. Okay, so we already know the sine square omega t will be equal to x square by a square. So substitute this relationship here, then that equation will become omega a square root of 1 minus x square by a square. Then cross multiplying the a square here, I can rewrite the equation as omega a root of a square minus x square divided by a square, or else, sorry, no need of equal to in between. So I can again write the equation as omega a multiplied by a minus l x root of a square minus x square divided by a. Then this will cancel. It is omega is equal to root of a square minus omega will be equal to root of, sorry, omega a square minus x square. Okay, now we know this equation, this is v equal to, right, v equal to. So in order to avoid this square root, we will square the both sides of the equation. Okay, let me find the eraser first of all. Okay, so we know that v square must be equal to omega square after squaring omega square multiplied by a square x square, a square minus x square, right? We can take out the omega to here. So v square divided by omega square is equal to a square minus x square, dividing the whole this equation throughout using the a square. So what we can do, that this is v square, or we can write v square omega square and divided by a square, right? V square omega square a square must be equal to this one will be a square divided by a square, hence it can be treated as 1 minus x square, sorry, that needed to be written properly. So 1 minus x square by a square. Okay, 1 minus x square by a square, and if I am taking this part, that is x square by a square, to the LHS of this equation, the equation will become, let me clear this first of all. So v square by a square plus x square by a square is equal to 1. So this equation is identical to x square by a square plus y square by b square is equal to 1. This is the mathematical equation for an ellipse. So you can see that these two equations are similar to each other, and you can see that the terms, this is the semi-major axis, this is the semi-minor axis, here both are having the same value, hence your ellipse will be somewhat like a circle, or else this equation you can write it like what, v square plus x square, taking the common a square outside and taking it into the RHS here, that is equal to a square. So this one also relatable to the equation of a circle, x square plus y square is equal to r square, where r is the radius, here a is the radius. So that's the only difference. So this will become a circle. Hello sir, so can you hear me? Hello, so can you hear me? Hello, so can you hear me?
Yeah, Krishna, I can hear.
Okay, so can I stop here?
Yeah, sure, sure. No issue.
Okay.
You can stop here and log out. We'll just contact you, right?
Okay,
Thank you very much, Krishna.
thank you sir.